And that simple harmonic motion gives us a way to think about how we're going up and down. So when we start to move into waves, we want to think of a pulse that's going in the wave. So if we're looking at that, if we've got a string and we have that string across, and I send a pulse, each little incremental part of the string or those little masses, they're going up and down like a simple harmonic oscillator. So what we're going to do now is we're going to take that and we're going to move it along in a linear direction. So we have lots of different waves. We have lots of waves. You can throw a pebble into the pond and you can get these ripples. But there's some things I want to point out about this picture with the ripples. You can get this constructive and destructive interference. So we can add waves together. So that's one thing. The other thing is that the waves are going to radiate out. They're going to move out as a circle, or for sound, it's going to move out as a sphere. So we're going to actually have it grow in its radius. So that's one of the things that's going to be about our features. So we have two types of waves. We have mechanical waves and we have electromagnetic waves, which is one of the reasons I like to start our chapter or start Physics 2 with the waves, because we're going to see those waves again at the end of the semester. So we've got both mechanical waves and electromagnetic waves. So we've got those pieces working. So the general features of waves is waves are in motion and they can transfer energy over a distance. And we know that. If I stand in front of a subwoofer, I'm going to feel it. If you hear a percussion explosion, you're going to feel it. The energy is transferred over the distance, but the matter is not. For example, if I've got that pulse in the string again, my little mass is going to stay right put where it was in the string. It's not going to move away. So we're not moving that way. So mechanical waves require a disturbance of some type. That could be my voice. That could be the speaker moving in and out. That could be a flick of a string, but I've got to do something to get it started. And the medium, the elements of the medium can be disturbed. My atoms can be disturbed. If I'm doing a longitudinal wave for sound, I can get increased density and rarefication, increased density and rarefication, but I can move my little air molecules. And I have to have that physical connection to have it move over. So you'll have those. So our pulse on a string. So looking at our pulse, we get a bump, we get that wave moving, but now our wave is moving in the X direction, right? We're getting that wave moving in the X direction. And this is our pulse. And we can actually have it move along. So we can do that. Our string is going to be under tension. So the speed of my wave is going to be impacted by the tension and the mass of my rope. But this is also called a transverse wave. So if I get that sinusoidal pattern that we can see, that's a transverse wave. So we look at how this little point moves as the pulse goes through. This is before the pulse goes through. This is at the top of the pulse. Go back. At the top of the pulse. And this is after the wave is propagated through. So transverse waves move perpendicular. All right, they move perpendicular. Longitudinal waves, they're going to compress and relax, compress and relax. So you can show both a transverse wave and a longitudinal wave on a slinky. I can see both of those. And so you get that displacement there. But waves, of course, can be made up by combinations. I can have transverse and longitudinal, think of earthquakes. I can have all of those things. And in fact, there's my earthquakes. I can get for my primary, I can get the other ones, and we can see both transverse and longitudinal waves. But my pulse now, when we were dealing with strictly simple harmonic motion, my pulse was only dependent, or the position was only dependent in that up and down, or that round and round, or my X or my Y. Now I have to account for the fact that my wave is moving. So we're now going to have a function of position. So we're going to look at our wave as a function of position. And so now we can look at that vertical and how does it transfer. Now the velocity of my wave is going to be the wavelength times the frequency, but we're actually going to get our quote waveform equation, but it's going to look very similar to what we saw for our simple harmonic motion. And you can go in there, still got our sinusoidal wave, and it allows us to have a simplified model. So so we can actually pull that together. The crest of the wave is going to be our maximum. The trough of our wave is going to be our minimum. And our wavelength is one complete cycle, crest to crest, trough to trough, equilibrium to equilibrium. Period is the time that it takes to complete that full cycle, just like what we saw before, and the frequency is equal to 1 over the period. And those are in units of hertz. And so ultimately, we get this equation that now I have both in position as well as in time. What we worked with before was strictly with time, as we were looking at that bobbing up and down. We were looking at that bobbing up and down. So we now have we've expanded our waveform equation a little bit. So we still can do the things that we've had before. We can rearrange in terms of wavelength. We still have our amplitude, and we can talk about, is it moving to the right or is it moving to the left? And you can look at my velocity of my wave is going to be the wavelength divided by time. And now I can express a wave function. So we can see that again. And we see that before. And so things are still exactly what we had before. And I still have a phase constant, because where's my wave exactly starting? I don't have to start precisely at 0. And I'm going to get that same information that I was seeing with my simple harmonic motion. And so those are our primary expressions. That's basically what we have. So we got sinusoidal waves on a string, which is going to allow us to get standing waves. And when we're starting to deal with points or with sound, we're looking at resonances. We're looking at our standing waves. We're looking at waves in a string. We're looking at waves in a pipe. And so we'll have a lot of those. And we can see those same functions that we were having before. We can convert to have it turn out that we're in velocity. And you guys don't have to worry about this. This is because that's calculus. You don't have to worry about it. You only have to worry that, yep, we got our equation that we saw, just like we saw in simple harmonic motion. And yep, we got our equation just like we saw in simple harmonic motion. My maximums are, my velocity maximum is still going to be my frequency. And this is my angular frequency times the amplitude. My acceleration is my angular frequency squared times the amplitude. And we've got that transverse point. So you've got that part. Tension is important. And so the speed of the waves in a string is going to be dependent on the mass of the string and the tension, just like you'd expect. You know, that's what we would expect it to be. So you would have that there. When we have our pulse hit a wall, we're going to get a reflected pulse, and it's going to flip over, and it's going to create that reflection. And again, these are things, when you think about it, you go, yeah, I know if I take a rope and I go like this and that other end is attached, it's going to come back that way. We see that reflection is there. Our wave is the pulse. If I've got a free end, so this is a free end, this is allowed to bob up and down, it's not going to come back inverted. because I can have that flexibility of moving it in there. So we can have boundaries. So you can have two different types of string come together. There's a light string and a heavy string. You'll see a change in the pulse. Again, something that you expect. Now, I think I only have a couple of homework problems about looking at the tension in the string or looking at those pulses. I've done more conceptual type stuff for you all, but I like to cover it so that you can see what's happening. But when you get it, you're not going to see something on a test about this kind of material. You just want to know that it's there, and we can transverse the waves. So I've got these in there. Now, energy of my waves, just like energy in my simple harmonic motion, we're going to have those energies as well. And we can actually deal with what the power of our wave is. And because again, the wave is going to transmit the energy. And we derive this stuff so that we can talk about the ear, and we derive it so we can talk about intensity. We derive this so you can see how sound is going to radiate out, and we're going to have those different pieces. These will come into play if you're doing radiography or sonograms. You're going to dive into this a lot more detail. But for this, we're just showing you that that's what's available. And we get our linear wave equation. So I'm going to skip through that and get to where we're talking about sound, because that's really where we wanted to go. So sound requires a medium, which means it can be air, water, all of those things. It is a mechanical wave, and it's longitudinal. And we characterize sound into three classes. Audible, that sound that we can hear with our ear, that's our audible sound. Infrasonic is below the audible range, and ultrasonic is above the audible range. And we're doing that solely based on humans, because elephants can hear infrasonic. That's their ears tuned a little differently. So what is our sound doing? We can look at it as a piston in air, and we're going to use that rarefied extension, rarefied extension, rarefied extension, which allows us to do the same wave equation that we saw in a string. The only difference is I've got a longitudinal wave versus a transverse wave. Now, we can actually look at this as a change in pressure. And pressure and power are going to be related. And that's what's going to happen when we actually utilize our ear. We're going to see a difference there. So I can do the variation in my pressure is going to change, but I can relate that back to what the material is. So if I'm dealing with water, it's going to be a little different. If I'm dealing with air, it's going to be a little different. And so we can look at our pressure in terms of cross-sectional area, and we can go through all the gory detail, and we can talk about impulse, where we get our impulse to come in. But basically, we're going to see something very, very similar to what we saw with a string, except now you're dealing with a bulk modulus and a density versus a tension and a linear density. So it gets you to the same place. But we can actually look at it a little differently, and this is where it's really cool. We can look at the wave velocity is going to be dependent on the elastic property of the wave, tension, bulk modulus, something along those lines, or it's inertial, over its inertial property. But because that elastic potential is there, sound has a temperature dependence, and it comes and it's related to our dealing with that elastic property. So sound at 0 degrees C is 331 meters per second. Sound at room temperature is usually about 343 meters per second. And you can convert back and forth. You can go convert back and forth. I'm going to skip that. So there's the speed of sound in a variety of mediums. that you can see those changes. And there's our air at 343 and our air at 0 degrees. So you've got those pieces. So we can do mechanical work, but that gets us to our power, because we want to get to power because we want to talk about intensity. And intensity is going to get us our decibels. Because remember, our human ear is a really sophisticated instrument. So we can do this power average divided by the area. And I'm going to go ahead and move on because I want to show you that as my sound moves out, it's going to go over as a 1 over R squared. All right. And we want to measure sound in decibels because human hearing goes from 2,000 hertz to 20,000 hertz, several orders of magnitude. But when I'm looking at intensity and what our ears can hear from an intensity point of view, we're going from the threshold of human hearing, that the smallest, tiniest sound that we can get, we're at 1 × 10 to the minus 12 Webers per meter squared. Our threshold of pain is 1. You are 12 orders of magnitude over that range for human hearing. We got to have something to deal with that. And that's why we use the logarithmic scales. So we can convert back and forth between our logarithmic scales and intensity, and we're able to look at those pieces. So here it gives you our sound levels and dealing with our frequencies and where things are. A rock concert is around the threshold of pain. Rocket engines, we've got lots of things that are out there for sound. In Blackboard, you have examples about how to add logarithms. In your appendix of your textbook, I would recommend you go look at how to work with logarithms. You've got a couple of homework problems where you're going to have to add how, if you put in 4 trumpets, what's the sound going to be like? So that's one of the things that you have. The Doppler effect, we have to worry about the Doppler effect. Most of us are familiar with it. We've all heard it. So in our book, they go through and when we draw the pictures. So if we're both stationary, we're going to hear the same frequency. But if we're not, so this observer, as this source of the sound is moving closer to that observer, you can see that these are getting tighter and tighter and tighter, while these are getting bigger and bigger and bigger. So you have 2 different types of conditions. You have the conditions when the observer is moving and the source is stationary. And you have the condition when the source is moving and the observer is stationary. And then you have the condition where you have both going on. When you're working these problems, you're wanting to be very careful to keep track of what frequency is the one that's moving and what frequency is the one that's not. Mach number, this gives us where we're going to break the speed of sound, so you can actually see the breaking and the speed of sound. It actually is very visual when you look at it. And then we can add our waves. That was our superposition. So this just shows you mathematically that you can add your waves. And we get that. But that's where we're going to start to get our resonance for standing waves. And there's your standing wave. So we're going to define this part of the wave as my antinode. This part of the wave is my node. This is one complete wave. All right, this is our standing wave. This is one complete wave. And basically, we're getting constructive interference. So our nodes, we can do it in these integers, depending on how many places that we get. And our antinodes give us our maximums. We can add our waves together, and that gets us our harmonics. So this would be the fundamental harmonic for a string between two fixed points. As we move through, this is our second harmonic. I now have one full wavelength. This is my third harmonic. I have 3.5 wavelengths. And we can find the natural frequencies based on the tension in my string and the length of my string. You can do the same thing in pipe. If I have two open-ended pipes, I get my antinodes at the open ends and I get my nodes at the closed ends. So I get my antinodes and nodes and we get the same kind of resonance items that's there. So things that aren't covered in this particular PowerPoint, and I know I went through it fast, but I've got individual little snippets and lectures where I've talked through a lot of these things in much more detail. But we didn't talk timbre. Timbre is the color of sound. That's why an oboe is going to sound different than a cello. I can also talk about pitch. Pitch is related to the frequency. Intensity is related to loudness. And then there's a thing called beats, which is if I have two frequencies that are very, very close together, you're going to hear a wah, 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 wah between the two, and those are beats. And those are descriptors of sound. So like I said, I know I went through that fairly quickly. Some of that material you didn't really need, but you do have, and if I go back to the various videos that you have, I've gone through them a lot slower. This one is a similar PowerPoint that you have in here, and it's a lot slower, talks about the interference and constructive and destructive, shows a little bit more of the rarefication that you get, links you to various things that are there, hits some of those same types of points that we were dealing with, but in a little less detail. This one actually shows the calculations of doing our decibels, looking at our point source. So it's just another way to look at the material. Talking about the Doppler effect, I have different pictures that you have, and then you've got different equations. So I'm going to stop there. I'm going to ask if anybody has any questions.